Chapter 11, the Nervous System, Integration and Control, Screencast 2. Now, one of the things that I have a tendency to preface, I want us to think about this. The nervous system is not a simple system. And also, let's kind of think about this. This is one of the major control systems that's responsible for controlling the entire body. So there really is no way that this can actually be considered to be a simple system. Now, when we talked about neural tissue previously, there's two general cell types. We have neurons themselves, and those are the cells that are actually responsible for generating electrical signals. And then we have the support cells, which were the glial cells. Now, when we look at the neurons, once again, they're characterized by generating what's known as action potentials. And an action potential is the electrical signal that's generated by neurons. And so the generation of these action potentials is the primary means of communication throughout the entire nervous system. So we'll be introducing potentials, and this is one of the more difficult topics. So this is I'm going to have to work a little bit on this. Now, we're going to go back to the sodium-potassium pump. Now, there's a couple of things that I want us to remember, and this is going to be critical. Sodium is the primary extracellular ion, and what that means, we find that outside the cell. Okay? Potassium is the primary intracellular ion, and so there's going to be a couple of things here that are going to be really important. Now, electrical flow is based on the movement of these ions, okay? Because remember, we're talking about charged particles. Now, we talked about the sodium-potassium pump previously, and one of the major functions of the sodium-potassium pump, aside from maintaining cell volume, is keeping the inside of the cell negative with respect to the outside. And that's what we call the resting membrane potential. Now, this is a difference in voltage across the cell membrane, and in a neuron, it's basically about negative 70 millivolts. Okay? You don't need to memorize that number, but this concept that the inside is negative with respect to the outside. And remember what the sodium-potassium pump does? It pumps out 3 positive charges for every 2 positive charges that are pumped in. So there's a net loss of positive charges, helping to maintain that negative membrane potential. Also, when we kind of talked about the cell membrane, remember there are a lot of different proteins. So protein channels were one, some were voltage gated. We're going to talk about those quite a bit. We have leak channels. There's a lot of leak channels for potassium. So that means it's pretty easy for potassium to leave the cell. Okay, so there's really a lot going on here. And what we want to remember for now, the inside of the cell is negative with respect to the outside at rest. Okay, we also want to remember our primary extracellular ion, which is sodium, and the primary intracellular ion, which is potassium. These are the players. Okay, so we'll come back to those rather extensively. Now here we can actually see the sodium-potassium pump and how that basically keeps things negative. So let's kind of take a look at what our frame of reference is. So this is outside the cell. This is in the axon, okay, of the neuron. And remember, the axon is the transmitting end. Okay, we've got a dendrite, that's the receiving end. The cell body, that's primarily where we're going to see the control center. So here we're within the axon, and notice that inside is negative with respect to the outside, and we can see what the sodium-potassium pump is doing, okay? So here we have the general flow. Sodium wants to come in, potassium wants to leave. And the sodium-potassium pump is going to be pumping out 3 positive charges for every 2. So that's a net loss of 1 positive charge. And hopefully you can see how that's going to keep the inside of that cell negative, because think about how we spend money. Most of us have more money going out than coming in. So we have a check balance in negative. That's what the cell is doing here. Now, we talked about action potentials. Not a lot, okay? But let's introduce graded potentials. Those have to happen first, okay? You cannot get an action potential without a graded potential. Now, graded potentials are these transient local changes in the resting potential, and they're generally caused by some type of a stimulus. Okay? And so one thing that's important to remember here, what a graded potential can do, it can either depolarize or hyperpolarize the membrane. And we'll see this terminology as we go through. Now, summation, this is a property that's characteristic only of graded potentials. You cannot sum action potentials. So you can actually, with graded potentials, they can be summed in space or time. And what this allows things to do is take multiple sensory input to get to know what is threshold, which is what's necessary to actually initiate or generate an action potential. Now here, I'm going to spend some time kind of focusing on a couple of things. So here we are at rest. Now, whenever you see a positive, okay, notice positive is depolarization, and you're basically kind of taking away that resting membrane potential. Here is hyperpolarizing, and what that's doing is notice, here's our threshold, okay? You're actually further away from it, so hyperpolarized. Here we have summation, and what we're looking at here is basically the summation or adding together grading potentials. Now, we continue to see a summation here, and look what happens when we actually get to threshold. There's our action potential. So that action potential is a very, very large reversal, okay? And look at the amount of electrical activity here, okay? It's very, very significant overall. So this is a really important diagram. So you want to understand what happens with depolarizing. So here you're getting closer to threshold, so this might be considered excitatory. Here, okay, you're further, so we might consider this to be inhibitory, okay? There's that characteristic that's specific only to graded potentials, which is summation, okay? And now there are some other characteristics of graded potentials that we want to kind of keep in mind. And I like using the example of an earthquake, okay? The shock waves are greatest at the epicenter, and as you get further away, okay, they get smaller, okay? So that's important, okay? The other thing I want us to remember here is these graded potentials are typically going to go in all directions. They're not going to go up, they're not going to go down, they kind of go everywhere. Now, there are going to be some characteristics that force them to go in a single direction, and we'll talk about that a little bit later, okay? Now, these are some terms that you want to be very comfortable with. So threshold, that's the point that you need to get to for an action potential to take place. Another way of describing an action potential is, you'll hear the term all or none. Okay? You don't get half an action potential. It happens or it doesn't happen. If you get to threshold, you get one. If you don't get to threshold, you don't. Now, depolarization, so now this is where I want you to spend some time to think about what's going on. We have voltage-gated sodium channels. They're going to open. Now remember, sodium wants to come into the cell. So sodium is going to rapidly move into the axon. So the depolarization phase of an action potential in a neuron is caused by sodium moving in. So all of a sudden you have a great amount of positive charges coming in. So there's your reversal of potential. Now, repolarization, this is about going back to rest. So now the sodium channels are going to close, potassium channels are open. Now potassium is going to move out of the axon. So these are positive charges that are leaving, and this is actually going to bring you back to rest. And actually there's going to be what's known as a hyperpolarization phase. Now, when all the channels are closed, so my voltage-gated sodium channels are closed, my voltage-gated potassium channels are closed, the sodium-potassium pump, which is going on all the time, that's going to basically take over, okay, and it's going to restore resting membrane potential, bringing it back to rest, that negative 70 millivolts. So let's take a look at this diagram. Okay, so here we kind of have the players. So here's depolarization. There's that sodium coming in. And then we can basically see that large influx. Okay, don't worry about this orange line. This is talking about permeability, and I think that's kind of confusing. Okay, so basically we see that threshold coming in, and there's that depolarization. Okay, threshold was reached, sodium influx, and we get that overall. Then repolarization. So now I've got those voltage-gated potassium channels are opening, and that's going to result in potassium actually leaving the cell. Okay, so as those positive charges leave, I'm going to go further and further down. Now I actually become hyperpolarized. So here was rest, and notice I'm a little bit more negative, and that's due to the fact that voltage-gated potassium channels, the gates function very slowly. Okay, so the gates function slowly. Kind of imagine a hydraulic screen door. You take that door, open it, and it takes a while for it to close. So while that gate is open, those potassium ions are leaving, and that results in that hyperpolarization. Then, once again, everything closes. Those voltage-gated channels, okay, are going to close. Sodium-potassium pump, which is always going, results in going back to that resting membrane potential. Now, as I said before, okay, action potentials are all or none, and another term is self-propagating. Okay, so if threshold is achieved, then that action potential is going to be generated. Okay, now another characteristic of action potentials is that they are identical in size. Okay, remember what I talked about graded potentials? As they get further away from the source of the stimulus, they actually get smaller. That doesn't happen. Okay? The other term we have to keep in mind here when we're talking about action potentials is self-propagating. So it's not the same action potential moving down the axon. Excuse me. What you want to think of, imagine set up a row of dominoes. Each one of those dominoes is an action potential. When you knock one down, it knocks down the other, and so on. And notice all those dominoes are the same size, they look alike, and so that's how action potentials are propagated. It's not the same action potential moving down the axon. You keep on generating them as you move down. Okay, that's really important. And as I said, they're identical in speed and amplitude, which is the size. Now, the other term that you might hear is they don't degrade, whereas graded potentials do degrade. Now, one of the things I want us to remember here is when we start talking about threshold, okay, if you have a stimulus that is way above threshold, it's not going to change what the action potential actually looks like. Okay. What may happen though is if you have a very, very strong stimuli, that is going to result in more action potentials per unit of time. Now, I'm going to get a little ahead of myself. And one of the reasons why I'm spending time with this and why action potentials are so important, ultimately, these action potentials result in the release of neurotransmitter from the terminal axon. Okay, and I'm going to say that once again. The eventual role of what an action potential is to actually release neurotransmitter. Now, the other thing that we have to kind of take a look at is conduction velocity, or how fast or the speed of these action potentials. Now, within a particular neuron, it's going to be the same. Okay? Now, depending upon other neurons, there's two things in particular that are going to impact conduction velocity. One, the diameter of the axon. So kind of imagine, okay, during the summer, there's a lot of construction going on, and you lose a lane, right? The road becomes narrower because construction is being done, and that's an increased resistance, and that slows things down. Think of a neuron the same way. If you've got a big, wide diameter, there's not a lot of resistance, and that's actually going to result in that action potential moving very quickly. Smaller diameter axons have a greater resistance, and that's going to slow things down. The other thing is going to be myelin. Okay, so we'll talk about that right in a little bit.